Hey everybody. Today we're talking about goodness of fit testing, asking whether a hypothesized distribution of a categorical random variable is plausible or not in light of sample data. We're going to approach this topic through an example. I want to imagine a large university that claims that their statistics classes are made up of 50% freshmen, 30% sophomores, 10% each juniors and seniors. And we want to test that claim using some sample data. That is, we want to test whether this hypothesized distribution is a good fit for the sample data we're going to obtain. The null hypothesis is just that the population has the stated distribution. So in this case, that the statistics students at this university have the breakdown that they're claiming. The alternative hypothesis is going to be very broad, just that the distribution doesn't follow this breakdown. Again, we're going to use sample data to decide between those two possibilities. So imagine we go out and get a simple random sample of size 65, and we find these counts: 28 freshmen, 24 sophomores, 9 juniors, 4 seniors. Obviously, this data doesn't break down exactly according to the distribution that the university claimed. Is that evidence against the university's claim, or could it just be due to random chance? The perspective we're going to have here is to look at the difference between the counts that we actually observed, like 28 freshmen, and compare that to the counts we would have expected when the null hypothesis were true. In a sample of size 65, if we're supposed to have 50% freshmen, that means we would expect 32.5 freshmen, compared to the 28 that we actually observed. Similarly, we expect 19.5 sophomores, 6.5 juniors, and 6.5 seniors. So I'm doing 50%, 30%, 10%, and 10% of 65. A test statistic that will be useful to us should measure how different the observed counts are from the expected ones, sort of overall. This test statistic is going to do the job. We're going to take the observed counts, subtract off the expected counts and square the results, and then divide by their respective expected counts. We're going to do that for each category: freshman, sophomore, junior, senior. Add up all those results. The statistic, chi, which I'm calling chi squared, is never negative. E is positive, and of course the square in the numerator of that formula is always going to be positive. And it can only be 0 when all the observed counts exactly match the expected ones. When the observed counts are more different from the expected counts, this test statistic gets larger. So the larger that this chi squared value gets, the less compatible the data is with the null hypothesis. When the null hypothesis is true, this test statistic has a chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories. So in this example, there are four possibilities for that categorical variable, so we're going to be in the distribution chi-squared of 3. And then we can compute a p-value from that test statistic using the CDF, the cumulative distribution function, of that chi-squared distribution. So let's actually compute the test statistic for the data that we have. Starting with the freshmen, we have an observed count of 28, an expected count of 32.5. So observed minus expected squared over expected, 28 minus 32.5 quantity squared, all over 32.5. I repeat that procedure 4 times, add up all the results. In this case, I get a chi-squared test statistic of 3.58. And that's supposed to measure how far our data is sort of overall from what's expected under the null hypothesis. Now, it's a little hard to interpret. We're better off actually computing a p-value and using that to make our ultimate decision. When conducting a goodness of fit test, we always compute the p-value using a right-tailed probability, the probability of randomly getting a value larger than the test statistic we observed just by random chance in the chi-square distribution with k minus 1 degrees of freedom. And the reason for this is that larger values of chi-squared indicate that the data is less compatible with the null hypothesis, representing stronger evidence against the null. This probability should always be evaluated using technology. I use R, where the command for the cumulative distribution function in a chi-square distribution is p chi-squared. That gives a probability to the left, a left-tailed probability, the area under the graph to the left. To get the area to the right, like I need for this p-value computation, I have to do 1 minus p chi-squared. I feed it my test statistic 3.58 and the number of degrees of freedom, 3, and I get a p-value of 0.31. So, in the situation where the null hypothesis is true, we'd still get data like this or more extreme, in other words, more different from the expected values, about 31% of the time. This is high for a p-value, so the data does not provide good evidence against the null hypothesis. The null hypothesis being that students at this large university in statistics classes are 50% freshmen, etc. Now bear in mind that this large p-value does not prove the null hypothesis. It just fails to provide evidence against it. We sometimes say that the data is compatible with this distribution, with a hypothesized distribution. Looking back on this process, let's summarize the steps that you follow when you're conducting a goodness of fit test for the distribution of a categorical variable. These exactly parallel the steps you follow in any hypothesis test. First, state your hypotheses. In a goodness of fit test, the null hypothesis is always that the variable follows a claimed distribution, like the one we had in our table. And the alternative hypothesis is just that it does not. Next, we compute a test statistic, in this case a chi-squared test statistic, and we do that using the formula sum, O minus E quantity squared over E, where O means the observed counts in the different categories, and E are the expected counts under the null hypothesis. We use that test statistic to compute a p-value. We always do a right-tailed probability in the distribution chi-squared of k minus 1, where k is the number of categories. And then finally, we use that p-value to make a decision about whether to reject the null hypothesis or not. We should always try and state a conclusion in language that a non-statistician can understand. Let's wrap up with a few words about when it's appropriate to use a chi-squared goodness of fit test. First of all, as with any hypothesis test in a college statistics course, you need to be in a situation where the data is coming from a simple random sample. In particular, all of your observations need to be independent from one another. Obviously, we're in a situation where the variable in question is categorical, so really the third bullet point on this slide is the important one for us. We need expected cell counts to be at least 5. There's something magical about the number of 5, but that's a good rule of thumb. Basically, if some of the bins are likely to be empty or nearly empty, the chi-squared test statistic won't give an accurate measure of goodness of fit, and you need a more specialized technique.